All right, it's time to move into the next part of this chapter, which is going to be focusing on bonding and how structures form. Mostly covalent is really what we're going to be talking about. But before we get into covalent, we're going to just do a little bit with both ionic and covalent. Up on the screen, you see a periodic table. I just want to make sure everybody remembers how you can quickly determine how many valence electrons atoms have based on where they are on the periodic table. So if you take a look, anything in this first row is going to have one valence electron. Here we're going to have 2 valence electrons. This whole column is going to have 3. Carbon's group 4, nitrogen's group 5, 6, 7, and 8. And of course we could figure that out using its electron configuration, but it's a lot easier if you can just look at the periodic table. You won't really need to be worrying about the ones in the middle of the periodic table. Most of the stuff we're going to deal with is going to be in the main group, and that has to do with the fact that most of the stuff we're going to deal with are going to be our nonmetals, and so you notice they are all over here. So I just want to refresh your memories on that before we get into Lewis dot diagrams. Now, Lewis dot diagrams are not Lewis structures. Lewis dot diagrams are just dot diagrams. They're super simple. Probably would never see one of these on an AP test, but just as a quick refresher. So if we find lithium on that periodic table, lithium's in the first group, so it has 1 valence electron. So its Lewis dot diagram would look like this: 1 dot next to lithium. You can put the dot anywhere. If you wanted to put it on the top of the Li, on the other side, or on the bottom, no big deal. Okay. There are rules about where and how you're supposed to place them, but again, this is too simplistic for them to ever put on the test. We're not going to focus our energy on that. Aluminum has 3 valence electrons, so again, any combination of 3 dots around aluminum is fine. If you paired one up, that's fine. It doesn't really matter as long as there are 3 dots. Phosphorus has 5 valence electrons. If you look at phosphorus on the periodic table, sorry, let's see if I can find it there for you. All right, so you see phosphorus there on the periodic table right here. So it's got 5 valence electrons. So we're going to put 5 dots. Oops, I just did too many. Okay, there we go. 5 dots. Again, doesn't matter how you put them. Chlorine has 7, so we're going to have to put 2 on each side and then 1. And then argon has 8. So again, it doesn't matter where you put them, just put them in no more than 2 on each side and use the top, bottom, left, and right side. So that's the idea of Lewis dot diagrams. Now I wanted to show you those Lewis dot diagrams because I want to also look at bonding and kind of think about what's happening when atoms bond. If we drew the Lewis dot diagram for sodium, it would look like what you see here on your paper. And if we drew the one for chlorine, it would look like what you see here on the paper. So if we were talking about the bonding between these two, you can see that sodium wants to give its electron to chlorine, like so. And that's why sodium ends up with a +1 charge, because it lost an electron, and chlorine has a -1 charge, and voila, we have a great relationship here. So that's ionic bonding. So that electron actually moved over to there. For covalent bonding, though, they want to share. You notice each chlorine has 7, so what will work out best for them is if they share an electron with each other. Then both of them end up with 8 electrons. If you see, this one has 8 and this one has 8. It just happens that they're sharing 2 of them. This type of bonding, this covalent bonding, is what we are going to be focusing on in this lesson. Okay. Now, if you flip your paper over, on the back side, there's some notes up at top. I'm not going to really read them to you, but I do want to go through the top part, which are just the types of bonds that we have. So we have what we call single bonds. We can represent a single bond either with pair of electrons, a dot pair, so that's showing that those 2 electrons are being shared between the fluorines, but more commonly we use a single line. So a single line means 2 electrons, okay? It's a lot easier than having to continue to do so many dots. So whenever we're doing bonding, we're using single lines. You can see that these right here are double bonds. So each one has 4 electrons that are being shared between those elements. And these are not completed structures by any means. I haven't finished them. This is just showing you the bonding. So we have single bonds like this one. We have double bonds like these ones. And then this is a triple bond. And a triple bond is 6 electrons. So every time you draw a line, you're representing 2 electrons. Now, the rules and steps for how to draw a Lewis structure are there on your paper. What we're going to do is use some examples to go through those, but realize the rules are always there, so you can always go back and look at them if needed. So the first thing we're going to do is count up our total valence electrons, okay, the total valence electrons. So nitrogen contributes 5, if you look where nitrogen is on the periodic table, and each hydrogen gives 1, but there's 3 hydrogens. So we have a total of 8 electrons to work with. From here on forth, don't try to use this as just dot diagrams. Don't try to figure out how to make the puzzle pieces fit like we did with that chlorine example. Think of it as you have 8 electrons in order to satisfy everything's octet. If you remember, everything wants to have 8 electrons around it. So what our goal is to get that to happen. So in following the rules, the next thing you're going to do is put whichever element you have the least of, which in this case is nitrogen, in the center, and then you're going to surround it with the other element. So in this case, 3 hydrogens. Okay, so I have my nitrogen in the middle and 3 hydrogens. The next step tells you to connect all the outside atoms, which are the hydrogens, to the inside atom with a single bond. So we're going to draw a single bond in between each one. Now remember, a single bond is 2 electrons. So thus far we've used 6 electrons here. Okay, 6 electrons. So we had a total of 8, and we've used 6. Next rule says to put any extra electrons you have on the outside atoms, so to fill their octets. Now we said everything wants to have 8, but a very important exception to that is hydrogen. Hydrogen only needs 2. If you look at where hydrogen is on the periodic table, it only has first energy level, so 1s, and so there's only room for 2 electrons. So hydrogen's octet really is 2 electrons. So actually, these hydrogens are all good. They all have their octets, or 2 electrons full. Next rule says to take any extra electrons you have and place them on the center atom. And we always put them on in pairs. So I'm going to put them like so. So now I've used all 8 of my electrons. Let's check and make sure that everything's octets have been satisfied. So let's start with, see if I can get this to do what I want. So if we look at the hydrogen, hydrogen here, and hydrogen here, they all have 2, which is their 8. They're 2 electrons, so they are satisfied. And then I look at nitrogen. If I look at what he thinks he has, although he's sharing, he thinks he has 8 as well. We have 2 from each of these single bonds that are right here. That's a single bond. Now it looks like a double bond, sorry. Okay. Those are all single bonds, 2, 4, and 6, and then this extra pair right here makes 8. So we've satisfied the octets. Everything is good to go. Now there are a couple more rules on the paper if you are following along with the rules. But in this problem, we don't have to go any further. Once everything's octets are satisfied, then we are finished. Okay, let's take a look at another example. Again, we need to see some other scenarios because that one worked out nicely where we didn't even have to think about everything. This is a chlorine and an oxygen. So chlorine, so see how this is a chlorine. Some people think it's carbon and iodide, but it's a chlorine. So chlorine has 7. If you look at oxygen on the periodic table, it has 6 valence electrons. And then this -1 is saying that we have an extra electron, right? A -1 charge is indicating an extra electron. So I have 14 electrons to work with. 14 electrons to work with. So those 14 electrons that I have, I'm going to use to satisfy the octets. Now, this one, we said before, we put the one in the middle that we have the least of, but we only have 1 chlorine and we only have 1 oxygen. So it doesn't really matter which one you choose to be as the center atom. We're going to use chlorine as our center atom, but if you had done oxygen, you'll get the same answer. So I'm going to think of this one right here as chlorine as my center atom. All right, so I'm going to connect everything to the outside atom using a single bond. I'm going to fill the octets of the outside atoms, which in this case is oxygen, with enough dots to make 8. So there I've got up to 8 for my oxygen. I've used 8. I have a total of 14, which means I still have 6 left. Next rule says to place any remaining electrons on the center atom. So like so. Okay. Center atom. Now I need to check my octets. So if I take a look here, I have got 8 on my oxygen. I've got 8 on my chlorine. So I'm actually good. You don't have to circle these, by the way. You're just looking, but I'm trying to help you see it better. So this is actually the structure for ClO with a -1 charge. But one very important thing, in the structure, you still have to write the charge. So you're going to put the charge in the upper right-hand corner, like so. Okay, so that is that one. Again, we didn't have to do a number of rules on this one. We'll see those extra rules on this last example. So let's do NO2 with a +1 charge. So nitrogens each contribute 5. The oxygens each contribute 6, and we have 2 of them. And then this plus is telling you to lose an electron. So we have a total of 16 electrons. Okay, center atom. is the one that you have the least of, so it'll be nitrogen. I'm going to put oxygen here and here. If you wanted to put them on top and bottom, that's fine too. Just as long as they're around the nitrogen. Now I'm going to connect the outside atom to the center atom using a single bond. So I've used 4 of my 16 electrons. Next step is to fill the octet of the outside atoms. Like so. Okay, that one, and now I'll come over to this one, fill the octet. So notice both of my oxygens now have their full 8 electrons. Now if you count up the amount of electrons that we've used so far, we've used all 16. So some people will make the mistake of stopping now and saying, okay, I've filled the octets of those outside ones, I've used all 16 electrons, I'm good. But look at nitrogen. Nitrogen only has 4 electrons. That's not good. So what are we going to do? We do not have any more electrons. Remember, one of the rules, the next rule says to put any extra electrons on the center atom, but I don't have any more, so I can't do that. So what we have to do is take some electrons we've already placed, and we have to share them. There are options here on how to do this. So let's just go ahead and take a pair from the right oxygen. I'm going to take this bottom pair. It doesn't matter which one pair you take. And I'm going to move it so that it's a double bond there. Now notice oxygen still has 8. Okay, it has the double bond, which is 4, and then those 2 pairs that are on it, that's 8. Now that made nitrogen better. Nitrogen has 6, but it needs 8. So you're going to take another pair and make another shared bond. And again, it doesn't matter for right now as to which pair you take. So I'm going to take, say, that pair and put it there. Didn't matter which ones I took. So now I ended up with still 8 on my oxygens and 8 on my nitrogen. You also might have opted, if you were doing this, so let's see, we were here. Okay, so let's say you did it like we did it before. We took this pair and we moved it here. And then maybe you decided to take this pair and move it there. Count them up. Doesn't everybody still have 8? So technically that structure works as well. This is actually something called resonance that we're going to get into in a couple of days. But for now, if you had this on your paper, I would accept it. And if you had this on your paper, I would accept it. There's actually a third one too, where that triple bond could be on the other side and the single bond on the right side. So as long as you had one of those, it's absolutely fine. Okay, so that's the idea of bonding. Now, we have a lot more rules to cover, a lot of things that we have to look at in terms of this, but this is the basic idea of how to do these problems. You count up your valence electrons, you place whatever atom you have the fewest of in the center, you make a single bond from the outside atoms to the center atom, then you fill the octets of the outside atoms with your electrons. Any extra electrons you have go on the center atom, and then you take, if necessary, electrons from the outside atoms and move them to be shared if you still need to reach an octet of something on the center atom.